Hello students, welcome to another video of LearnGuru. So today we will be discussing about rational numbers. So last class also we have discussed about number system, definition of numbers, types of numbers, real number, imaginary number. Real numbers are divided into rational numbers, irrational numbers, and we have further classified rational numbers as well as defined rational number. So today we are going to study more about rational numbers. Now suppose any number, if it is given to you, since rational numbers come of different types, if a number is given to you, you should be able to identify the rational number. Okay, so these are the three steps which will help, or three points which will help you to identify a rational number. So first is it may be a fraction of integers. So how does a fraction look like? Give me an example of fraction. 3/4 is an example of fraction. What is the definition of rational number? Any number that is represented in the form of p by q, where q is not equal to 0, is called a rational number. Okay, so can I say 3 is equal to p, 4 is equal to q, and q is not equal to 0? From this, can I say? Yes. So can I say that fraction is a rational number? Yes, fraction is a rational number. But what is it written? Fraction of integers. So again, if you go to the, if you try to remember the last video, I have told that rational numbers are also divided into integers. Integers may be of positive integer or negative integer. What are the examples of integer? 1, 2, 3, it may be -1, -2, -3. So these are the positive and negative integers. So from that, what can you say? Is 3 is an integer? Yes, 3 is an integer. Is 4 is an integer? Yes, 4 is an integer. So what can we say? That fractions are rational numbers and the numerator and the denominator in the fraction are nothing but integers. Okay, for example, I can write -5/6. Is -5/6 a rational number? Yes, -5 is a what? -5 is a negative integer, 6 is a positive integer. Both of them are represented in the form of p by q, and q is equal to 6, that is not equal to 0. So we can say that fractions are rational numbers. Okay. Second point is it may be a positive or negative integer or 0. Okay. So while explaining you the definition of rational integers and explaining you the significance of fractions, okay, I have not mentioned that why integers are called as rational numbers. So doubt may arise in your mind. Examples of positive integers are like 4, 5, 1, -10, -100, any number you name, these are either positive or negative integers. Okay. Now how we represent these or call this as rational number? Because according to the definition of rational number, if I take example of 4, we are getting only the p part or the numerator part, but the denominator part or the q part is missing. How can we say that it is a rational number? Okay, so the answer to this is that, can I write 4 as 4/1? Yes, because any number divided by 1 is the number itself. To divide it by writing divided by 1 or writing the number simply means the same thing. So from this, can I say 4 is equal to p and 1 is equal to q and q is not equal to 0? Yes, so does it come in as a rational number, in the form of a rational number? Can you express this in the form of a rational number? Yes, so we can say that integers, either it may be either a positive integer or a negative integer. For example, minus 10 can be written as minus 10 by 1. So this is also a rational number, since it can be expressed in the form of p by q and q is not equal to 0. Okay, so this part I think is clear to you. Now what about 0? Okay, so 0, can I write 0? Okay, 0 as 0 by 1, we can write 0 as 0 by 1, or 0 by 100, or 0 by 20, or 0 by minus, we can write 0 in this form. Okay, so any number divided by 0 only means a 0 itself, isn't it? So 0, from this expression, can I write 0? Can I write p equal to 0? Yes. Q equal to 20. Q is not equal to 0. So is it satisfying the definition of rational number? Because it comes in the form of p by q and q is not equal to 0. So we can say that 0 is also a rational number in addition to positive and negative integers. Okay, come to the third point. Third point is written is that it may be a decimal expansion which is either terminating or non-terminating but repeating. Okay, now doubt may arise in your mind that how a decimal expansion can be called as a rational number, because decimal expansion, if you have some rough idea of how a decimal number looks like, it will be something as 0.5 or 5.625. So these are the examples of decimal numbers. So how this can be called as a rational number, because here also the same thing, we are getting only the p part, q part is missing. Yes, and if you come to this term, terminating or non-terminating but repeating, this is also very new to you. Okay, so let me tell you students, decimal expansion, any fraction can be converted into its equivalent decimal expansion. Okay, fraction is a rational number. If a fraction can be converted into its equivalent decimal expansion, so that decimal expansion can also be called as a rational number. Are you getting my point? So, decimal expansions are also rational number provided it is terminating or non-terminating but repeating. Okay, so what are those terms, terminating, non-terminating, and how can a fraction be converted into decimal expansion? We are going to see now. So to explain you how to convert fraction into equivalent decimal expansion, I have taken two fractions, 3 by 4 and 4 by 3. So first of all, I will show you how to convert this into decimal. After that, I will explain you the terms terminating and non-terminating but repeating. Okay, so let us convert this 3 by 4. Okay, so to convert a fraction into equivalent decimal expansion, so what you need to do, you need to divide the numerator by the denominator. So 3 divided by 4. So you are dividing the numerator by denominator. Okay. Now you see. 3 is less than 4. Yes, 3 is less than 4. So you can't perform the division at this particular stage. Okay, because for that you have to put a 0 and you have to give a decimal here. Okay. So 4 sevens are 28. 2. Again 2 is less than 4. Then again you have to put a 0. 4 fives are 20. Remainder is 0. Okay, now go to this expression. So to convert, again I am telling you, to convert a fraction into equivalent decimal expansion, you have to divide the numerator by the denominator. 4 divided by 3. So 4. So 4 is greater than 3. So 3 ones are 3. You are getting the remainder as 1. Again 1 is less than 3. So you have to give a decimal. Then you have to give a 0. 3 3s are 9. 9. Again you are getting the remainder as 1. Again you give this as 0. 3 3s are 9. 1 0. 3 3s are 9. 1. Okay, so up to this, let us pause this division, this particular case, come to this expression. Now if you see here, remainder, so do you know the parts of the division? This part is called the quotient, isn't it? This part is called the remainder. So you see that the remainder has come out to be 0. Isn't it? So as soon as the remainder comes to be 0, you are ending the process of division here. Isn't it? Means you are ending the process of division means what? You are terminating it. And another meaning of end is terminate. Isn't it? So you are terminating the division here, and the required quotient that you found, so that quotient is called the terminating decimal expansion. Terminating decimal expansion. You are getting a decimal number from this division. So for that, the number that you are getting is called a terminating decimal. Quotient that you are getting, decimal number that you are getting, that is called a terminating decimal expansion. When does this terminating decimal expansion occurs? When the remainder comes to be 0 and there is no further scope of extending the division. Understood what is a terminating decimal expansion? Now come to this example, 4 divided by 3. So if you see here, you are getting 1 as remainder, isn't it? 1 as remainder, here also 1, here also 1. So as the remainder of 1, value 1 is being repeated, you are, this 333, this is called as quotient, isn't it? So the value 333 in the quotient is also being repeated. And can you see any hope that this division remainder will come to be 0 and the division will end? No, there is no such hope, because this 1, you are getting the remainder as 1. Isn't it? So you can't end the division here. So this type of decimal expansion, okay, where the remainder never comes to be 0, is called as non-terminating decimal expansion. Non-terminating. And if you see, the remainder 1 is being repeated, and this quotient or 333 is also being repeating, isn't it? So can I say non-terminating but repeating decimal expansion? This decimal expansion is non-terminating but repeating? Yes, we can say that non-terminating but this is decimal expansion is non-terminating but repeating. Okay, so this is the practical difference between terminating decimal expansion, non-terminating decimal expansion. So we will be studying more about these two terms when we proceed chapter wise. Now I am giving you, for 2 to 3 lectures, I will give you only the concepts of real numbers or rational numbers. After that we will go according to the chapters in the NCERT book. Okay, so this is the practical difference, means just to identify the types of rational numbers. If a rational number is given to you, you should be able to identify. For this I have explained you these two terms. I hope these two terms are clear to you. Now I will take some other decimal expansions to make you understand about these two terms much better. Here I have taken 4 decimal expansions. Okay, so you are to identify which one is terminating and which one is non-terminating. Now come to this expression 0.625. So 0.625, from this you can say that after 5 no other digits has repeated. From that we can conclude that the remainder has come out to be 0 and the division has ended, has been terminated, and you are getting 0.625 the quotient as the decimal expansion. So we can write this as terminating decimal expansion. Okay, I am just writing terminating. Now 0.333333. So here clearly you can see that 3 is being repeated. Means what? The value of remainder has been repeated and the division has never ended. So we can say that it is non-terminating decimal expansion, and since 3 is being repeated, so we can say that non-terminating and repeating. Okay. Now 0.3333 means that 3 is being repeated. So can I write, instead of writing 3 for several times, I can write 0.3 bar. So it indicates that 3 is being repeated. Okay. Next 1.375. From that what conclusion can you draw? What conclusion can you draw? Yes, this is a terminating decimal expansion because after decimal no numbers is being repeated. So decimal has ended because the remainder has come out to be 0. So for that I will write that it is a terminating decimal expansion. It is a terminating decimal expansion. Okay. Now come to this particular example. Here you see that 5, 6, 7, 8, up to this no same numbers are repeating, but after that again 5, 6, 7, 8. From this we can say that a sequence of numbers are being repeated. Yes? Isn't it? So that also we can say that since the sequence of numbers are being repeated, so from that also we can conclude that it is a non-terminating and repeating decimal expansion. So instead of writing 4.5678 for 5.678, we can just simplify it by writing as 4.5678 bar. Okay. Now with this particular term, with this particular things, another term comes into picture that is called as periodicity. Periodicity means the numbers that are, how many numbers are being repeated in the decimal expansion. So from here 3333 means what? Only 3 is being repeating, means what? 3 is under the bar, or in simple word the number of digits under the bar represents the periodicity. Here so the periodicity is 1. For in case of this example, periodicity is 1. What is the periodicity here? 1, 2, 3, 4. How many numbers are under the bar? 4 numbers are under the bar. So here periodicity is 4. So periodicity comes into picture only for only for non-terminating and repeating decimal expansion. For the terminating decimal expansion, this term is completely meaningless, because here, since no digits are being repeated continuously, sequentially, so we can say that the periodicity is 0. Okay, for here also periodicity is 0, for here also periodicity is 0. So periodicity term exists only for non-terminating and repeating decimal expansions. Here we come to the end of this class. I think today's lecture was helpful to you. If you find this video useful, please subscribe, like and share it with your friends and relatives. So take care. Thank you very much.